Hello there. Once you have a number of z-scores, what you might try to do is to find the difference between the two z-scores in terms of the proportion or percentage between them. This can be helpful in a number of situations, but let's say you wanted to know the proportion of difference in terms of percentile ranks between your grade and someone else's grade. You could take the two z-scores and calculate the proportion between them and then convert that into a percentage. There are a couple ways to do this. In fact, there are two ways you have to do it for two different scenarios, and then a third way you could choose to do it if you wanted. The first and easier way is when we have positive z and negative z. So one of each. For here, we have a couple of steps. First, we need to find mean to z for both z's. Then we go on and we add both mean to z's. Then third, we get to celebrate because we got to do this the simple way. So how does this look? Well, I'm glad you asked. Let's go on and pick out two z's. Let's say the first z, which we'll call z1, is equal to 1.63, and our second z, z2, is equal to negative 2.01. What are we going to do for our mean to z? Well, let's put it up here. And then we'll just put our values up there, right in here. So we're going to need a statistical table for this, like the ones we used for finding values before. I happen to have them in the back of this textbook. There we go. So I've already talked a little bit about this, so let's just go ahead and find our values. Neither is on the first page, but they're both on the second page. We're looking for 1.63, which is here, which has a mean to z of 0.4484. Then we get to look at our other z, 2.01, which is all the way here at the bottom of this page, you can see here, which has a mean to z of 0.0778. Excuse me, 0.4778. Almost got myself there. Move it over just a little bit, 0.4778. And we can set this textbook aside for now. So what are we going to do next? We're going to go back up here. We're going to add our mean to z's together. So we'll label this as step 1. This is step 2. We're going to take 0.4484 plus 0.4778, which is going to give us 2.629. So 0.9262, or if we wanted to convert, we could say 92.62% of the values in our distribution fall between our upper bound of z is equal to 1.63 and our lower bound z is equal to negative 2.01. Now, some of you may have noticed that I use the positive version, just 2.01, and use that information for negative 2.01. This is because our tables refer to the proportion between the z and the mean. And that's the same for positive and negative values, that we won't have any differences between positive and negative z's in terms of the proportion between them and the mean. So our z tables traditionally only include positive values. Now, when we're talking about proportion, our proportion isn't negative. It's just, well, let's use green here. When we're looking at our distribution, that's an okay drawing, close to normal. But when we're looking at our distribution, this half is equal to 0.5000, and this half is equal to 0.5000. The proportion between 2.01 and negative 2.01, they're going to fall at the same area. That would be right about here. They're both going to have a proportion of, let's use black again so it stands out, both going to have this area in here between these two lines of 0.4778. 0.4778 is just that the negative above here on the z-score itself tells us if it's above the mean for positive or below the mean for negative. The proportion itself is not affected by the sign of the z-score. All right. Now we've done this the easy way. Let's go on to the more challenging version. We're going to deal with either two positive z's or two negative z's. So how does this work? Well, first, we have to make a choice. We can find, we can do 1.1 and then 1.2. So we find mean to z for both, or we find beyond z for both. When we come down to step 2, we're going to again have our choice. So we're going to subtract, and we can again make our dichotomy of 2.1 and 2.2. So we subtract the mean to z for the larger z minus mean to z for the smaller z. And I'm thinking that's going to be pretty tight, so let's add in a line so we don't get our directions mixed up here. For the second part, we take beyond z for our smaller z minus beyond z for the larger z. And that's going to give us the proportion that falls between these two values. So let's go ahead and calculate that. Go ahead, grab a little blue, separate it out. Whoop, not blue at all. Let's head to blue now. So step 1, and let's do the 1.1 version. Because we already have our mean to z's. We already have, where did I set them? There they are. We already know that z1 is equal to 0.4484. I should probably put that where you can see it, but 0.4484. And that z number 2 was equal to 0.4778. Now, we had these two, and since we need to do both positive or both negative, I can do one of two things here. Since this was equal to z is equal to 1.63, and here we have z is equal to 2.01, I can either call this a negative because it doesn't affect my proportion of mean to z, or I could turn this into a positive. It doesn't matter. I'm going to go, however, with both positive. if for no other reason than positive. So now we're going to take the mean to z for our larger z. So this is our larger z, 2.01. And we're going to take 0.4778, and we're going to subtract our smaller z, or the proportion that corresponds to our smaller z, so minus 0.4484, which is going to give me 4,920. So 0.0294 falls between these two z-scores. That is our answer. Go ahead and bring this color back. Now, you might be interested in seeing this for the other version. Well, we can do that. We can go beyond z instead. Just draw some lines here, rack off this space, and we'll use black. So we can find our beyond z in two different ways. We could go to the tables and look at our beyond z column for each of these values, or we could say that since each half of our table, or rather each half of our distribution, looking here, is equal to 0.5000, I can take 0.5000 and subtract my mean to z, and that will give me the area that is beyond my z. And since you've seen our tables, I'm going to go with this version. So 0.5000 minus 0.4484 gives me my beyond z, so z1b is how I'll abbreviate it since I'm short on space, is equal to 0.0516. My z2 beyond is equal to 0.5000 minus 0.4778 is equal to 0.0222. Now, if you're dubious about this, go ahead and check in your z tables, and you'll find out that these are the correct numbers, that they correspond exactly to our beyond z column. So that's step 1. Now let's head on to step 2. Step 2 is we're going to take beyond z for the smaller z. So we're going to take, this is our smaller z, 1.63. So we're going to take 0.0516 minus the larger z, so 0.0222, which is going to give me 492. 0.0294. You'll see that this lines up exactly with the proportion we got doing it the other way. And that's because these get you to the same place. It's just a choice on if you want to deal with the mean to z or the beyond z. So whatever you prefer. Anyway, there you have it. This is how you calculate the proportion or percentage of space between two z-scores. And this works for individual z-scores or z-scores for groups, because the z-score for group adjustment has already been made in calculating the standard error of the mean, so we don't have to worry about anything here. I hope this has been helpful for you. You will find these, as always, down in the description, and I hope that you'll let me know if this has been useful for you, or if there's something else that would be useful for you as you're going through classes or working on your research.